Hello, everyone. Welcome to this mini workshop, which is called Statistical Physics at 65. I am glad to see all of you here in the room, but also lots of people connected online, so hello. I hope you will enjoy this workshop. So this is called Statistical Physics at 65, but of course everybody knows that the reason for that is to celebrate some career of our friend Raúl Toral, and that happens to be 65 this year. Why 65? Most of you are Spanish, so you know that 65 was the usual retirement age in Spain. Now this is no longer the case, and so we are glad that Raúl will continue with us sometime. I don't know how much, but anyway, 65 can be interpreted as a nice number of the form 2 to the n plus 1, or is also one of the Stirling numbers of the second kind, or it's one octagonal, is the fifth octagonal number. So there are several reasons to put 65 in the title. But probably the most important of them is that it points at, it selects an initial condition for a trajectory. It's the initial, so you put 65 years ago from now, then you go to 1958. So this is the starting condition for the career of Raúl Toral. He was born. And okay, so this was the initial condition. Then the trajectory developed, and there has been many items in this long trajectory. I just will mention a few of them. He got the PhD in theoretical physics from the University of Barcelona in 1980, and then a PhD in 1985 under the supervision of Joaquín Marro with a thesis called Nucleation Theory in the Proximity of a First-Order Phase Transition. I am glad that during this time of his PhD, he was my first teacher in quantum mechanics, or the second one, but the first one is better to forget about him. Okay, after his PhD, he got a NATO fellowship to go to Edinburgh to work with Professor Wallace. Was from until 87, and then he moved to Temple University in Philadelphia to work with Jim Ganton until 1890. In 1989, he got a position of professor titular, permanent position at the University of the Balearic Islands. In 92, he got a position as investigador científico at CSIC, and he worked in the then Institute for Advanced Studies in the Balearic Islands. And in 94, he got a position of catedrático at UIB. The range of the topics which Raúl has worked are huge, large. I just mentioned some of them that are listed in his CV: phase transition dynamics, critical phenomena, stochastic processes. He has a book with Pere Collet on that. Fundamentals of statistical mechanics, so even Sally's statistics has been touched by Raúl. Monte Carlo methods, hybrid Monte Carlo, polymer physics, surface absorptions in surface, disorder effects, constructive effects of disorder, resonance induced by diversity, by disorder, phase transition induced by disorder. So the disorder has a big role in the career of Raúl. Also synchronization of systems with delays, stochastic processes with delay. And lately, he has been doing a lot of work on dynamics of social systems. He has well over 200 publications, 2 books, the one of stochastic numerical methods with Pere Collet, and also a book with Joan Cerdà, Introduction to Ordinary Differential Equations. Even he has a patent, which is called Procedure and Apparatus for the Control of a Master Dynamical System, and of the order of 100 invited talks, organizer of over 30 conferences. Important, 14 PhD theses has been supervised by him. That's a very interesting point. And okay, he has done many other things. Was the director of the Master of Physics of Complex Systems here at IFISC. He received the award for the best teaching article in publication of the Real Sociedad Española de Física. Was president of GFNOL, the thematic group of statistical and nonlinear physics in the Physics Society of Spain, member of the board of the Statistical and Nonlinear Physics Division of the European Physical Society. Okay, lots of things and many data, many numbers, but the most important thing is that we all know that it's a great pleasure to work with Raúl. That's really good for all of us. He has been a very important person in the career of many of us and in the personal life of many of us, and we are happy that he will not retire yet. Now, he will give the first talk of this workshop, and after this forward career he has followed, he will talk about something about backward trajectories and how this can also be used to learn something. So, Raúl.
Okay, thank you, Emilio. Well, is that working? Yes. Thank you very much for this kind words. Well, those who know me know how uncomfortable I am right now here, okay? I don't like to be the center of attention at all, I never like so. But still, I'm very grateful to you, okay, for coming, for setting up this event. I'm very moved and I really appreciate your coming here. I should start before my talk, whatever it is, about thanking so many people, okay? I should start from the beginning, not from 1958, a little bit later, by thanking my supervisor, Joaquin Marro, from whom I learned many things, physics and other things that I cannot tell you what it is about. I learned many things from him. And he was always a very supportive person. I remember that I would go to his office at whatever time of the day, and whatever he was doing, I would bump into his office. Hey, look what he did. And then he looked at me, okay, set aside whatever he was doing something, and listen to me whatever time. He never said no to us when I talked to him. So I really appreciate this attitude, which I have tried to keep. A second person which I would like to mention as my mentor was Jim Ganton, my second postdoctoral stay. Again, I learned many things from him of attitude, not just physics. Physics is for granted, right? I learned things about the attitude towards life. And, you know, my wife knows that many times we ask, how would Jim do that? So we will try to, we are very sorry for his passing away not so long ago. Then I should move on. After the postdoctoral stage, you look for a permanent position. And then I was very glad to be given by Maxi the opportunity to come here. He told me about this position, which wasn't for me, as we used to say, right? So this position was not for me, but still I got it. And I have been so glad to have come here. I mean, it has been extremely fruitful in terms of relationships. I would not like to mention people, I mean, because I will forget somebody, okay? So I remember Emilio and Pera were there at the time. They were the two students of Maxi. Claudio and Horacio was also around. Claudio arrived a little bit later as a postdoc, and then so many other collaborations. I have learned that, at least in my experience, in this field, as in every other field, there are good people and bad people. There are morons and extremely helpful people. I'm not sure I'm a moron for somebody else. I'm not saying I'm the good one, okay? But what I have learned, at least for me, my experience, it's easy to keep away those people you don't want to interact with. So I just surrounded myself with the people that I like, and whatever people I dislike, simply, you know, forget about him or her. That's my experience. I don't know what. So this is a good thing about this. I mean, the pay is not so, the payroll is not so high, but I mean, this is a good thing. Another good thing, at least for me, that I never had a boss. I never had someone telling me what to do and do that, and you have to work on this and not on something else. And of course, I have to try to keep this idea with my students, which I'm again very grateful to my students. Starting from the first one, Thomas Sinter, who is over there, to the latest ones, Javi, Sarah, and Juan, who is over there, and David, who is over there, and Parite. who is. Okay. I will learn from them. I hope they'll learn from me. I try to be, again, not bossy. I try to help them and not to tell them, not to force them to do something. You know, when you write a thesis, you feel obliged. You feel obliged to say something good about your supervisor. Okay, acknowledgement. You can say many things that probably are not true. But I remember one from one particular student, which I liked very much. And in that particular student said of me that I was reliable and uncomplicated, which I think is fantastic. That's what I want to be. Okay, perfect. I want to be reliable. You can trust me. And I like simple things. I like simple things in life, and I like simple things in physics. I think in science, everything has to be simple. I always struggle to find the simplest explanation of everything. You can explain something in 2 lines, don't use 3. Okay, keep it as simple as possible because it's so complicated already, and that you know, keep it simple. Keep it simple is one of my mottos in life. I think it's everything. Last but not least, my family. Of course, in this job, you are alone many times. Okay, and you feel that you have many doubts, especially at the beginning. But all the way, you have many doubts of whether you will be able to do it or not. And having someone there supporting you is very important. Of course, my wife, Tony, who most of you know, some of you know, has been very helpful. And it would have been much more difficult without her. Again, of course, my son, who came late, and to whom I used to read Patria at night for sleeping. I hope it did not cause him any trauma. he seems okay. Okay, so now I should start after this. I hope I did not forget anything. I don't forget anybody. And I should talk about. I did not know what to talk about really. Should I summarize everything what I did in my life? Explain what I'm doing here right now in general with my students. So I just decided to focus on a topic. And again, I'll try to give that very simple to give you some ideas. Already 15 minutes, so probably will not have time to do this. But the first thing I did is to think why 65. Emilio has given already a reason. I mean, we have 10 fingers, right? That's why we like 10, 20, 100. Someone is 100 years old. Okay, that's fantastic. We celebrate those numbers. But you know, some of us like another language. You know, there are this number of types of persons. Okay, who's going to find those? Okay, so I always had the theory that we should celebrate 1, 2, 4, 8, 16, 34, 64, and you are very lucky, 128. And that will be it, okay? That's the numbers. But then today you remind me that I'm this number. I'm 1000001 years old, so otherwise known as 65. And this is a remarkable number because it's a palindromic number. It represents forwards and backwards. And you know, we like to call those things otherwise. We call it a reversible number. Something which is reversible. But you know, of course, in physics, we know that things are not reversible. Okay? They have a direction of time. So fortunately, we cannot go back in time. We always move forward in time. But I will show you how a problem treated backwards can give us interesting information about the forward process. Okay, that's the idea. That's one of the topics I'm working on at the moment. Again, I have been collaborating with many people. I would not like to mention them, my current students, but I don't want to mention specific names. I did have the temptation about okay, some of you know what I'm talking about. I will talk the origin of the n factorial in statistical physics, but I leave that talk to a less controversial moment. Okay, so the moment you have been waiting for, without any further ado, the Botter model. Yeah. I know you will enjoy that. This is the simplest problem of non-equilibrium statistical physics. You cannot have anything simpler than this. Okay? You know what it's about. It's voters, individual, having 2 opinions, +1 or -1 or whatever, a favor or against. And then you have a simple rule. A randomly chosen voter takes the opinion of one randomly chosen neighbor. So simply, you know how it works. It's to copy the opinion of a neighbor. And there is one question, only one question. One model, one question. Is consensus reached? How does the reaching of consensus depend on the network of interactions? That's all we ask. Given this rule, will everybody go to the same opinion, to the same state, or there will be a mixing of states? Okay? And we want to measure, to know whether we reach consensus, we need to define consensus. There are two measures of consensus. One is the magnetization, and the other is the density of active links. How many links join nodes in different states? Okay? If this number is 0, all of them are in the same state, you have reached consensus. So when is consensus reached? And that's the answer. Because of the stochastic dynamics, consensus being an absorbing state, once you reach that, you do not get out. And ergodicity, there are no forbidden states. You can reach all of them. So eventually you will reach the absorbing state and you will stop there. So consensus is always reached in a finite system in a finite time. Problem solved. Thank you very much for your attention. That's it. Wait a minute. Have a few more slides. The key words is that you reach consensus in a finite time, in a finite system. Because the universe is finite. Okay, the universe has a finite time, and as far as we know, finite space. So something could happen during this duration. So how long does it take? And we have learned that in this model, in some occasions, we have dynamic and metastability. So states that do not reach consensus, this is the density factor limit, do not reach consensus for a long time, and then eventually, of course, they will reach. They're obliged to do that. It has to. So eventually, you reach consensus. And if you do that many times, you see that you reach consensus at the stochastic times, you complete the average, as we like to do, and you feed that to exponential, define a sub-average time, and you find that for dimension greater than 2 and some other complex practices, this scales as n. So if n is large, you reach consensus after a long time. Okay. And this situation happens in other models with absorbing states. We all are expert epidemiologists by now. Okay, after these 3 years, we all know this epidemic model. So I don't need to explain what this is. You have an infection, in which a people infects a healthy individual, they both become infected, and then an infected can become healthy at some rate. And you have a population, and you know that given the previous rules, that this will come to the extinction of the illness, not of the population, the extinction of the illness. The illness will disappear because consensus, everybody being healthy, is an absorbing state. If everybody is healthy, then no one can infect anybody, and this cannot evolve anymore. So this will go to extinction, as it's called, okay, to extinction of the illness. But how long does it take to go there? Well, at least 3 years. But you know, the time of, you see this interesting paper by Nassel, highly overlooked. It says that the time to extinction does very strongly with R0, the basic reproductive number, the ratio between the infection and recovery rates. It is rather small, independent of n, the number of people, if R0 is less than 1. But grows exponentially, yes, exponentially in this case, with n if R0 is greater than 1. It can then really easily exceed the age of the universe, even for a small population. So this model predicts that the illness will last forever, which is not what happens, by the way. So this simple model needs to be improved. But let's take this simple model and say that we consider that you will have a number of infected people for a long time, and then eventually, yes, it has to. So we will go to the extinction state. So these are trajectories that go to the extinction state. How do we do those trajectories? Well, that's what I will tell you. Okay, we can do many of those trajectories, and people are really interested. People have studied how the trajectory goes to the extinction state. So remember, before that, there is a long transient, extremely long, and then you have a trajectory that goes to the extinction. And people study that. This is the WKB theory, which I will not explain. But this is a prediction of how it looks. And you see our numerical simulations predict that this WKB theory is rather good for this problem. This is an example of rare events. Rare events are something that happens with a low probability. And rare events are important. They are rare, but when they happen, something happens. Okay, they are very, 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 very important. And you can have earthquakes, or have storms, And of course, we are not treating these models, and we like something closer. So we studied the perfect drunk. Okay, people that goes to the bar, have some beers, and then goes to right or left with some probability. Okay, and then you ask the question: will this person reach his home walking this way or not? Reaching his home will be a rare event, or what will happen? So this is a much closer, much simpler problem than studying any of those. That's the question, okay? Whether this person walking right and left will reach home. Home is an absorbing state. Once you reach home, his wife will not allow him to get out again. That's it. So this is. There are many other examples, which is the double potential. So you see that you have this relaxational dynamics with some noise, and then you will. This is not absorbing, but still, you will oscillate about one of those points. For a small noise and a small size, there will be many jumps from one state to the other. That's what you see there. You see trajectories that go one over there. But if the system size is large or the noise is small, you will oscillate around only one of the wells for a very, very, very long time before eventually jumping to the other one. Okay? The dynamics is symmetric. They will tell you from one to another. But when you look at one particular trajectory for a large system or small noise, that will be highly asymmetric. That will be only oscillated around. Symmetry has been broken by this system size. There are other examples. You have cells. The cells can be in two different states. And you can go from one state to another. And the cell can perform different functions in one of the states. And then you need to know the path that takes you from one state to the other state of the cell. And then again, it's a path that can go one way or another, can have a higher or lower probability. And then how do you study rare trajectories? Of course, you simulate rare trajectories. So you run your computer and you wait and wait and wait. Of course, it's rare, so you wait a long time. So what you have to do is to wait, and you take Nurduna to your limit and wait. Or you can build a bridge. A bridge is a trajectory that you force to start, a stochastic trajectory that you force to start at a given point and to end at another given point. You force the trajectory to do that. And bridges is not our idea, but bridges have been known in the, not so much in the physics literature, but in the mathematics literature, they have been known for some time. Mostly Gaussian bridges, bridges for Gaussian processes. And then we have here a way of building bridges for any stochastic process. Any stochastic process defined by a transition probability, and that's how we do it normally. Normally we go forward. Okay? You start with initial condition, and then you use your rules to advance in time with your probabilities. So you do it 1, 3, n times, and you get the probability distribution at the end. So our idea, a very simple idea, is to do it backwards. I like this because it's very simple. I mean, there are some mathematics. It's Bayes' theorem. It's extremely simple to explain. We have to do that backwards. So we start from the end. We set a point at the end. And then we go backwards with some probabilities, with some rate, which we call W tilde, that go from one state to the previous one in time. Okay? And we found a rule for generating trajectories with the same statistical properties going forwards or backwards. And the rule is very simple. The rates going backwards have to be the rates going forwards by this ratio. Extremely simple rule. And then we've applied this rule. We apply this to the drunken person, in which we know these probabilities, which are the typical binomials. So you can do that with all the extent, and of course it works very well. This is the trajectory you get when you go forward. Rare trajectories you don't get unless you wait for a long time. So you get only trajectories which are close to the origin. But when doing this process, you can generate all type of ending points. I mean, this is very rare trajectory. It's a trajectory where you only go right and right and right and right and right for so many steps, for 100 steps. It's very unlikely. That will never happen. But we can generate those trajectories. And the important thing, those trajectories have the same statistical properties than the ones that you would do in the forward process. So first, what can you do with that? You, for instance, compute the first passage time distribution. How long will it take the person to get to his house? And you can do that, Of course, there are some technical details, which I will not explain at all. And you can do that, and you can compute the first Parsetan distribution, and you can see that it agrees very well with some theory, and we are very happy. And we apply that to the SIS model. And this, remember, before that, there is a long transient, and then you have the trajectory that goes down. And this is a trajectory that we have generated using this method. And we compare that with the WKB solution, which is theoretical analysis, but we can, which is the WKB is deterministic solution. There are no fluctuations. We can compute also the fluctuations around this WKB solution. And the same thing for the 5-4 model. We can generate trajectories that go from one well to the other. Okay? Even though with the noise is very small, you will never see those trajectories in a simulation. In a numerical simulation with the level of noise, you will never observe that. Here we are able to observe that. What we do is to force the final point and the initial point, and then compute those from the Langevan equation. We compute the rates to go from one place to the other. And in this case, there is no theory. I mean, as far as we know, no one knows the shape of this trajectory, and that's one of the things we're working on, to identify, toward the theory of this trajectory and to compare with the simulations. This is another case that we do in the case of the cell differentiation that was part of Javi's thesis. We'll take this figure. We have this. This is the WKB. This is some protein concentration in the cell, X1 and X2. So you go from one state to another state. There are two different cell states, which the cell performs different functions. So this is the way how you go from one to another. This is the WKB solution, the deterministic, and you see all the color trajectories, the blue and the green trajectories, and the brown that go from different noise intensities from one to another. So we can see that, of course, you do not follow a deterministic trajectory from one state to the other. Backtracking, as we call it, seems to be a very powerful method to generate trajectories. All we need is this simple rule. Okay? So from a forward rate, you construct a backward rate using this rule. Of course, we need to know the probability distribution at all x all times. So the difficulty of the method is hidden here. So we need methods to use to generate that. How do we do that? Well, we solve the master equation, we solve the Fokker-Planck equation, we use to solve the master and the Fokker-Planck WKB approximation, whatever. In some cases, we can use what is called the quasi-stationary solution. The solution given the fluctuations around this metastable state. And we have also done that. And I would like to mention very briefly this thing about the weighted ensemble method, because I'm extremely happy. This is one of the things that I did with Lutz Szymanski-Geyer, which a collaborator who passed away recently, sadly again. This is a work that has not caught a lot of attention, to be honest. By the number of citations, it's not very high. But I'm very proud of this work. I like it very much. And this is just a simple example, is to generate the P of x of t, to generate the probability distribution at a given location, at a given time. This is for the random walk, for which we know the solution. Okay, we can compare. We have a method we call the weighted ensemble, which I will describe here, that gives you the probability distribution. Okay, so the line is the theory, and the dots are the result of our method. You might not be impressed that we are able to reproduce the binomial distribution, but you should look at the figure down in logarithmic scale. Okay, and then you should look at the scale of the limit. This is 10 to the minus 40. Okay, so we're able to determine the probability distribution or the binomial distribution with 40 digits of precision using that method. So this is a method that we have used in some cases. And what we're doing very recently, I would like to mention that, is that we call it the quasi-stationary distribution, which is when you have a master equation, you simply define the quasi-stationary distribution at the probability of something happening without reaching the absorbing state. It's a simple definition. Probability that you have n, the value of n, the n number of infected, of n number of voters in one opinion, non being zero. Just resisted to non being zero. Using, again, Bayes' rule, this is Pn 1 minus P of 0, and you can find an equation for Qn of t. And this is the equation, which I will show here, because I like equations. And this is the same form of the master equation plus an extra term, which is non-linear. So we have a set of couple non-linear differential equations. And we love that. Okay, that's a challenging problem, is to solve a set of non-linear differential equations that we'll be doing now. And we have made some progress. That's very, and this is last week's results. We have this for the SIS model. We have the dots are the result of numerical simulations or a numerical treatment of this process. This line is the result of the WKB approximation, which it doesn't work very well. And what we've achieved so far is this line that you see goes very close to the point. Still, we have some some error there that we're working on improving this number. So we can have a theoretical description of this quasi-stationary distribution. Okay, I'm finishing now. And as a summary, I really believe that the best engineer I have so many good collaborators and so many people, helping me, and so on. I'm sure that will be many more things. I don't know. I'm very positive about that, and of course, I will like you for the attention. Thank you very much.
Thank you, Raúl. So, time for some short questions.
You had 65 years to make those questions.
No questions?
Lalo is there.
Hi. Thank you. So the rule that you use to reverse the trajectory is kind of a Bayesian inverse of the forward, or?
It's an inversion of the forward process, yes. It's to define a Markov process with rates that go in the reverse direction.
Okay. And this exactly retrieves.
This exactly reproduces the. It's a very simple rule that we have. I say bridges are not a new concept, but this way of constructing bridges, as far as we know, is a new way. And of course, this is I wrote that in the language of Markov processes, but you can also do it in the language of Fokker-Planck equations and Langevin equations. We have extended this idea of how to reverse a process, keeping the same statistical properties and keeping the end. The final and starting points fixed. Mm-hmm. Of course, remember, you need to know the probability distribution. Okay, so it's very suitable for low-dimensional problems. As far as you have a high-dimensional problem, the problem becomes extremely difficult. That's why we're working on approximations to this probability distribution, like the quasi-stationary distribution, and that's why we are really focusing our.
Thank you.
Last question.
Yeah. I didn't get exactly what you get, for instance, in the bistable system.
I get the trajectories. I am able to
the probability distribution of the weighting of the jump of the transition time.
No, that's not. No, the transition time. Now you can ask any question that you want. For instance, you can ask which is the rate,
but not the time, because the time is the age of the universe. So this is
not the time of the remaining one. The time of the transition. How long it takes you to go from one to another? Okay, one, you have started the process. So the typical trajectory, which is the time, this thing, the time of the trajectory, which is the shape and time of the trajectory, not the time in one of the wells.
Thank you again. And now we pass to the second speaker. He is Pedro Garrido, and he will tell us that ghosts exist and can be used to make perturbation schemes to solve ordinary differential equations.
Thank you. I'm not good person to. Okay. No, visita no. Okay, sorry. I'm not a good person to publicly say many things, good things for people, but in this case, I think Raúl Toral is been a long time, a very good friend. I think that is has been a very inspiring person for me. I met him in 1986, I think, when he was finishing his PhD and I was finishing my graduate. And well, I think along the years we met in the States and many places. You know, it's like a happy family. when you are happy, you are a family. But no, I think it's a very good scientist, very inspiring, and very good person. And that makes life easy in this world. Okay, I choose that subject because because always they complain that I do very unuseful things, complex and useful things. But in this last year I was working on this kind of things that I motivate, and really at some point I said in which precise point I thought Raúl Toral, what he'll do, and I did that. No, okay. Yeah, it was okay, I think. Okay, this is a Gauss perturbation scheme. Okay, let's solve ordinary differential equations when you don't know how to solve them. Okay, that's the point. This is okay. Typically, we know that okay, there are differential equations, quantum mechanics, that are linear equations, and nonlinear equations like Newton's law. I don't know, three-body problem. No? But always we think, at least I think, that linear problems, that means that the differential equation, they're always linear dependence on the unknown. Okay, it's complex, but we have a lot of mathematical. I am talking about non-numerics in principle. Later on, I show numerics, but on trying to get things from mathematics. Okay, algebraically, solutions, real solutions. No, let's do a Runge-Kutta and this is solution. No, this is forbidden. Okay. Okay, then linear. We have a lot of theory. Stimuli theory. All of us we know how to solve the hydrogen atom. No, very nice. No, the harmonic, spherical harmonics and Legendre polynomial. That was very nice. A big theory, no, to solve this kind of differential equations. Very useful. Okay, but we have green functions. We have perturbation theory. Many things. What happens with nonlinear problems? That we are lost. Typically, if we are lucky, we have a perturbative parameter in the equation that let us to do, some approximation around some known solution. But in general, what happens if we don't have any perturbation parameter? That's the point. Then what do we do? Numerics. Okay, forbidden. But okay, I thought when I was young that was the way. Nonlinearities means complexity. Complexity means numerics. Okay. But many years ago, I always found this example that always for me was really hard, no? From the point of view of theory. This is the Fourier's law in 1D. Okay, we have a bar. Okay, we have a bar, one-dimensional bar with two temperatures fixed. Okay, and we want to know how evolve some temperature profile when T equals 0 is uniform, okay, and T greater than 0, we change, say T naught only, okay? And then this evolves, okay? Fourier knew or described all this process with this simple equation, okay? That means that the derivative over time of the temperature field is some derivative of some current. The current was proportional to the thermal conductivity, this kappa, and the gradient of temperature. Okay, and this is the boundary conditions. This equation seems simple, but it's not so simple. Depends, obviously, if theoretically, if kappa, how it is a function of temperature kappa. If you choose kappa equals 1, you have a linear problem, and this is the solution. It's not nice, but it's a solution. Okay, this has sum over infinite terms. Okay, but you solve the problem for any initial temperature, and you see this solution. This is the solution. This is time, x, and this is the field. How it evolves from flat temperature profile to linear final temperature profile. Nice. But real world is not kappa equals 1. If a gas has kappa proportional to a square root of T. But if you put the square root of T, that is a real world, then there is no algebraic solution. Look, if I am choosing boundary conditions 1 and in this picture 2. That means there is no perturbative parameter. The difference of temperature is very small, something like that. No. What was my problem? My problem was that if you do the linear, the numerical solution of this nonlinear case, here is also plotted the nonlinear solution. And this is the difference. Difference is around 2%. This solution, algebraic solution, is so near to the nonlinear one. How can access this nonlinear solution from this linear one? That's my question. But I have no parameter. I have no way to perturbate, to find this nonlinear difference. Okay? But what happens normally? When I was young, I discovered that all people in Navier-Stokes assume kappa equals 1. Why? Because solutions are so near. Why we introduce complexity in our problem? That was the way that I was thinking in that time. That okay, in some way, nonlinear problem is simplified by a linear one, but it's okay. It's a good approximation to reality. And most of the theoretical approaches in Navier-Stokes assume kappa equals 1. Okay, but I was unsatisfied because I wanted to really, coming from this solution, to describe the nonlinear solution. But for many years, I was in that thinking, and then I simplified the problem following Raúl Toral strategy, and instead to partial differential equations that you know that are quite hard and there's a lot of, I simplified a lot of problems. That means an ordinary differential equation, nonlinear, you know, this G, this H, with some boundary conditions, could be initial value problems. That means you give at some x equals 0, the value of the function or the derivative of the function. That happens in Newton's law evolution problems, or boundary value problems that you fix in the limits of your space, where you define the solution, some values. No? Doesn't matter. The problem was, given this differential equation, given a linear differential equation with parameters P0, P1, P2, P3, that we know how to solve it always. And the problem is, it's possible to build a systematic sequence of approximations to the solution of the nonlinear problem. It's possible with some nice properties. That means that at least the convergence is exponentially fast. For a very, very low convergence, we have Fourier transformation of these kind of things. Okay, that was the problem. And I give you the solutions because I have short time just for students to have the solutions. You can use it. And then why it works. This is for the next 5 years, when the 70s. I can give the solution of the Okay, this is the only slide. This is the method. Okay, that's very short. We have our nonlinear problem. Well, one, you know that for initial value problems, just some general ideas. For ordinary differential equations, you know that for initial value problems, if G and H are well defined, some Lipschitz conditions, then you have a unique solution and the solution exists. That seems trivial, but it's not so trivial because physicists sometimes don't remember, don't know, that boundary conditions, when you fix the boundaries in the space, for instance, then maybe could be that the problem has no solution, one solution, two solutions, or infinite solutions. There is no existence and uniqueness theorem. Just to know that this field also is very, of ordinary differential equations, very interesting. Well, the method, fast. This is my ODE, and I define a new ODE, ordinary differential equation, with the same boundary conditions. That is a linear operator, just second derivative, first derivative with constant in the front, and an epsilon that is my operator minus the linear operator. Trivial thing, that is a linear problem plus a perturbation. Say, okay, nice idea, no? Silly idea, of course. And then, but you see that if all the p's are 0, that means L equals 0 identically, and then you recover the original problem. Maybe you say, okay, then I do an expansion in epsilon, and then I go to p goes to 0. This is my original idea. Failed, disaster, of course. It's very, 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 I think when p goes to 0, the perturbation scheme breaks, it's not convergent at all. Then no way. But also you see that when epsilon equals 1, trivially also we recover the solution. Then, it was strange, no? But I did the following. I do a perturbation of this extended ODE. One makes a perturbative scheme, order by order, you get the solution. You can always solve the linear operator plus something, then you can solve it. You can do it explicitly algebraically. You have all the terms order by order. Then for order n, that means that you have n terms. You define yn when the sum is over k naught to n, but when epsilon equals 1. Okay, then you have this thing, epsilon equals 1. It's not a perturbative scheme, of course, but I have a free parameter piece that I can tune. Then how I tune? I define a distance to the real solution that is defined in this case. You have your interval, you apply to your approximate solution, you put in your differential equation to elevate to the square and average. That means that if it's the solution, this is identically 0. If it's not, it's something positive. Okay? And then with these free parameters, I minimize the distance and choose the parameters that minimize the distance. Then this method gives you a systematic way to approximate the solution, order by order, and exponentially fast. You say, cannot be. Okay, do it. I give you some example, one example. And this the example is this equation. It's very simple because you have, this boundary value problem. You fix I0 and I1 to different values, and this is the solution, exact solution. Why I choose that? Well, in the world of people solving ODEs with some numerics or algorithm, there are a set of equations that are used. It's in the web. I used to because they have some pathologies that the algorithms makes hard to to find the good solution. This is one of them, the simplest one, because you see that there are a combination of exponentials with minus x and exponentials with plus x. Algorithms with exponentials, positive and negative, means big numbers, small numbers. This mixture is not good for algorithms. Then I use this first trial. Okay, this is the method in the example. First, this is the extended ODE. This is the linear part, and this is the epsilon, the original equation, minus the linear part. Okay, that's all. This is the, I only use P naught, in the sense P0 as the linear width of y prime, P1, 1 prime, P2, because it's not necessary. It's an example, very simple. I do the perturbative solution. Okay, you get order by order the solution. You see that here the pathology, when P0 goes to 0, this breaks down. That means that this strategy of doing the perturbation and going P0 to 0 is a disaster. You go order by order, you get your solutions. You can do it in Mathematica and go to order 40 or 60, and you get all the expressions. You can do it by yourself, but also mathematicians, they don't like these algebraic programs, but are very helpful for physicists. That's very nice. Okay, you have your proto sequence of approximation that is the sum of these perturbative parts for when epsilon equals 1. This, you choose now the P0 that minimize this distance. Everything is algebraic. That means you can do it order by order. But I do it by Mathematica because it's very tiring. Order first or the second, okay, but order 13 is too much. But it's algebraic, and there is no approximation, okay? And can you see here the distance, the log in base 10 of the distance, okay? And then this blue point is what is the minimum of the distance, and this is another. These reds are other distance that I defined in the paper, but it's not. Okay, it's another distance, but it's not because I wanted to see what the sensitive was, the mechanism. You define different distances, but it's not. Okay, you see that? You see that how the distance, this is a log plot. This is the end of the order of iterations. How decay is an exponential. That means it's converging very exponentially fast. And you see the solution is the red one, and n equals 0 is the linear solution. 1, 2, 3, 4, 5. This is the, well, because we know the exact solution in this case, you make the difference between the in x of your solution, your approximation, and the real one, and do the logarithm, and you see that order by order in 20, I think 20 or 30 steps, you have a precision of uniform precision, that is important, uniform, up to 10 to minus 16. Okay, then that's good. I don't know if I have more time. How much time I have? 0? Sure. Okay, then okay, I'll forget it. That I go to the. Okay, you can use this method to solve initial value problems. Also, there is a problem because you have to minimize some distance. But the distance, when you have initial value problems, you have to give me a time, no, a time to look for the solution. And then, okay, for a given time, things work well. But if you want to have, a long time, because there's evolution of a rocket flying to Mars, and then you need, time, and the orbit could be very complicated. And then the convergence could be exponentially fast, but very, very, very slow. No? Then I just design some way that you fix the number of iterations, and the time is just the moves in the way that the precision that you choose is kept fixed, and then you see that you recover in some Lane Emden, that is another ordinary differential equation that you improve some way the numerics that Mathematica has in their packs. No? Okay, then properties of the method. One detects solutions just looking by a minimum of a distance. Important part, if the distance has no minimum, there is no solution. The distance may have several minimums. Then you have several solutions. Okay, you see that in many problems. Then you have algebraic solutions that you can work with. There is an error control. There is a spatially uniform convergence to the solution, and the most important part, there is a exponential convergence, fast convergence to the solution. What is the cost expansion? Means that I had a problem. Then I can think that from a linear initial operator, I can access to the nonlinear solution, and I have a method. And you said, what is the method? To create this perturbation, this scheme, order by order. And what is the parameter, perturbative parameter? It's something that is inside in some way in the problem, in the distance, how the distance behaves. Is the distance decrease like delta to the n, and this you can measure. And this is the perturbative parameter. Okay? Then, finally, you can take your Fokker-Planck, your Langevin, your nonlinear ODE, solve your linear equation with some parameter, the linear operator, and try to minimize a distance, and you get a systematic way to approximate solutions. Okay? Then, for theoretical people, okay, could be an improvement, no, in your life. And no numerics. Thank you.
Thank you, Pedro. Okay. One or two short questions and short answers.
I don't know.
Sorry, Pedro. I didn't understand what is the relation between the nonlinear equation that you have and the linear operator that you propose. Is whatever you want, or
no linear? You put the linear in the sense that is the operator that you know how to solve.
Okay.
Algebraically.
But you can propose anything, or it has to be related
anything. Now
with
you put your parameters P0, P1, P2. The linear operator, more general in the sense that if it was a fourth order ordinary differential equation, with a 4 derivative of y, and linear, because this constants, this p's, you are going to fix on minimizing the distance.
Mm-hmm.
I think. But it should be in some sense something that you know how to solve. It's no thing, no way. Okay.
Some other question? Have you tried several variables equations? Or?
No. Okay. No, but I am happy because I think it works in these cases that are typical, no, for algorithms. And then, well, first step.
Good.
Thank you.
Thank you. Now you know that the thesis advisor of Raúl Toral and also of Pedro Garrido was Joaquín Marro. Joaquín Marro wanted to come. It was we started to talk with him, but finally he has not been able to come. But he has sent a message for Raúl and for all of us. So let's see the video of Joaquín Marro.
Querido Raúl, me uno muy decidida y alegremente a la celebración de tu 65 aniversario, y no podía ser de otra forma, pues como tú sabes bien, he disfrutado de haberme encontrado contigo en los años 80 y de la relación que de ellos se ha seguido, aunque últimamente ha sido tenue. Supongo que sabes que naciste a la vez que la Comunidad Económica Europea, que ese mismo año se abrió el primer Carrefour Se desintegró en la atmósfera el Sputnik 1 y la NASA puso en órbita el Explorer 1. Fidel Castro hizo su primera locución en Radio Rebelde desde Sierra Maestra, asegurando que morirían antes que rendirse. El dictador Francisco Franco promulgó ante las Cortes sus leyes fundamentales del reino. Estados Unidos detonó medio centenar de bombas atómicas de prueba. Murieron Pío XII y Bertolt Brecht. Se inventó el Chupa Chups y se puso en marcha ARPANET, la red pionera que condujo al actual Internet. En fin, que te empeñaste con otros en dejar ese 1958 bien marcado. Ahora espero que no dejes tan marcado este 2023, sino que, dado que está siendo muy útil para la ciencia, sigas con tu actividad científica. Sigue, como hacen muchos amigos americanos. Yo no he podido hacerlo por no haberme vuelto a los Estados Unidos y me arrepiento. Nuestros organismos pueden llegar a mostrar alguna deficiencia para ciertas actividades. Por ejemplo, esto es en parte lo que me impide, muy lamentablemente, estar ahora allí contigo y con tus otros amigos. Pero estas deficiencias que nos trae la edad no son esenciales. Hemos venido desarrollando bien nuestras aptitudes cerebrales y, salvo accidentes, seguiremos un tiempo con aceptable potencia y agilidad mentales, además de disfrutar de una inestimable experiencia. Terminaste tu licenciatura en Barcelona en un año bisiesto y terminado en cero. No lo hacen muchos. Y precisamente cuando Indira Gandhi ganó las elecciones en la India, se descubrió el efecto Hall. La banda Queen lanzó con mucho éxito un disco en el que, por ejemplo, recuerdo Crazy Little Thing Called Love. Se creó en Polonia el sindicato Solidaridad. Ronald Reagan fue elegido presidente de los USA y se disolvió la banda Led Zeppelin. En ese escenario hablamos tú y yo y comenzaste una tesis doctoral que terminarías cuando el sandinista Daniel Ortega tomó posesión de la presidencia de Nicaragua. El gran evasor de capitales español Francisco Palazón, me parece que era, se fugó a Uruguay. La URSS eligió presidente a Mikhail Gorbachev. La Policía Nacional Española comenzó a admitir mujeres en sus filas. Se comercializó la primera versión de Windows y 60 miembros de una tribu filipina que habían fallado en convertir hojas de árbol en billetes se suicidaron con insecticida para poder ver la imagen de Dios. Ese mismo año, 1985, tú nos enseñaste en qué consistía la nucleación en cambios de fase discontinuos, un fenómeno que hoy se sabe muy frecuente, y llegaste a publicar entonces 11 papers en buenas revistas, que supongo que es un récord, o casi, aparte de otros 4 papers también conmigo que publicaste después, sin contar unos buenos apuntes docentes sobre escala dinámica y teoría ergódica. Te fuiste enseguida a Edimburgo, donde te quejabas de la falta de sol, y ya de vuelta a España, enamorado, te marchaste a las islas con Maxi, donde habéis creado un hub físico-estadístico partiendo de la nada. En fin, esto es lo que quería recordar, aparte de, como sabes bien, te deseo lo mejor de lo mejor para los próximos 65 años. Ahora vais a vivir mucho más. Un fortísimo abrazo para ti y para tu familia y muy afectuosos saludos para todos. Adiós.
Muchas gracias, Joaquín, si nos estás escuchando. Y ahora, para los que estamos en la sala, coffee.
Querido Raúl, me uno muy decidida
¿qué hago?
Ya sé que está,
O sea, yo
Tengo que ponerme aquí.
Ahí está bien. Aquí todavía sales, pero ya...
O sea, ahí, ¿no?
Aquí o si quieres estar por delante, pero bueno, por donde está la mesa.
Aquí, ¿no?
¿Detrás de la mesa o delante de la mesa?
Aquí. Este es mi...
So let's start with the second part of the celebration mini workshop. I hope that you have recharged your batteries with coffee and cookies. The first talk of this session is Juan Manuel Parrondo, a researcher at the Universidad Complutense de Madrid, and he will talk us about entropy.
Ya. ¿Esto funciona?
Sí. Okay, so thank you. It's a real pleasure to be here, of course, to be here in Mallorca, but of course to be in this big party in honor of Raúl. So, well, you see that I'm not as good as Raúl, and to figure how to write 65 in a fancy way. This is the best idea. or Emilio, know that you said that it is the sixth Stirling number or something like that. So my mathematical culture is not so big. That's the best I did. Okay, I was looking for pictures, photos with Raúl. I don't have so many. He has more because we share a lot of time in the pre-digital era, and I didn't have a camera. I guess I don't have any photo of a conference that we were in Australia and France and many places. This is the only one that I got, or the only one that Google Photos detected your face. So, and it is in the, you know where it is? This is very recent. This is in Argentina when we went to visit the Tigre neighborhood. Okay, I met Raúl, well, probably I knew him before, but we started the collaboration in 93 or 92. And we had a dinner in FISES, in the conference of Statistical Physics in Spain. And then we started a collaboration that was very, very successful. We had this paper, noise-induced phase transitions. We studied for the first time phase transitions in a system with multiplicative noise, an extended system with many degrees of freedom. And the paper has been very used in many places. We got citations from neuroscience, from agronomy, from all the places where you have something especially extended and then some noise, an out of equilibrium noise. So, and it is consistent. We still have a lot of citations in the last, so we share a lot of things. We have collaborated. We share also love for music. Well, he can do better than me. And we share also the love for physics, as he explained, for a very the simplest as possible way of explaining physics, and also a love for the foundations of statistical mechanics. Maybe not everybody knows that Raúl has very nice work on pedagogical aspects and fundamental aspects of statistical mechanics. So for today, I decided to talk about something very controversial somehow, and Pedro probably has something to say here, which is well, the definition of entropy. So it's very fundamental, and actually more than the definition of entropy, I would say that it is let's say the nature of irreversibility. This is the problem. This is the problem that I'm going to address here. And if you can find an explanation of irreversibility which is objective, which does not depend on the observer, this is the goal. And the solution, I will give you a solution, an objective explanation of irreversibility, but it's so simple and it's nothing new. It's something that goes back to Einstein. So this is what I also say, that it is. This talk is like a footnote in a textbook of statistical mechanics, so that nothing else. But it's a footnote that I'm kind of proud of it. So irreversibility is usually, or the problem of irreversibility is always explained with videos like this one. Here you have two gases separated by a piston. You remove the piston, and you see something which is irreversible. No, you cannot. If you reverse the movie, you see something that it is impossible to see spontaneously in nature. But if you zoom in, what you see is elastic collisions ruled by the Newton's law. So it's completely reversible. So the problem of irreversibility is how to make compatible this reversible behavior of or predicted by Newton's equation with the irreversibility. And the common wisdom is that irreversibility is an emergent property that can be seen in the macroscopic scale. So the macro is irreversible and the micro is reversible. I will show you that this is wrong, that irreversibility has nothing to do with the scales. It's something else. It has to do with fluctuations. The usual explanation that you see in many books is the one that Boltzmann gave. Boltzmann realized that a macroscopic observer doesn't see the details of the microstates. So if you have, this is the phase space, the space of microstates. What it is accessible to an observer is macrostates, which define regions in the phase space. And the second discovery by Boltzmann is that the size of these regions are disparate. There are one region occupies 99.99% of the phase space, and the others are very small. So if you start in a macro state defined or that occupies a small region, and if the system explores the phase space in a kind of a uniform way, just for probability reasons, you will finally get in the big region, which is the equilibrium state, and you will never go back to the initial condition. So this is the typical explanation by Boltzmann. The explanation had a lot of controversy, and actually it had it even until now, I would say. There is a paper by Joel Lebowitz in Physics Today, which was, I think it was very influential for our generation, and it was translated even to Spanish. And he said, no, Boltzmann gave the solution to the problem of irreversibility. I don't know if you can read it, but it says, given the success, I cannot read it from here. Well, he says in the first paragraph that that Boltzmann solved the problem, so that you don't need, I think this sentence is, I see no need for alternate explanations. So the solution is there. And I agree with Lebowitz, he's right, but he, in the same paper, he mentioned one problem, which is the definition of macrostate. I told you that a macrostate is what is a macroscopic observer can access to, and so on. And he said there is some kind of arbitrariness. What is this macrostate? And he said, but this should not concern, but arbitrariness did concern me. This is my problem. My obsession is what is the crossover between micro and macro. And is there any objective way of defining macrostates? And this is the problem that I had for many years. And the question is if we can define macrostates in an objective way. And I will give you the solution, which is, as I said, it's not very new. It's not really new. Sorry. It's Joel, no? Dan Frankel did this once that he got a call from Clausius. You remember this talk? Okay, so let's just, well, here everybody's expert in statistical mechanics, so I don't need you really to mention this. This is the Boltzmann explanation. He introduced the entropy as scale law of the size of each region. And then if you go to the regions which are the biggest, the biggest in the phase space, you go to the state with the maximum entropy. But the problem is how to define macro states in an objective way. Well, the solution, or the one that satisfies me, is that you have to forget about, you have to focus on observables. You have to forget about observers or macro states or something like that. You just look at observables. And what is an observable in classical physics is a function of the phase space onto real numbers. So here you have the energy of one particle. If the system is the air here in this room, one observable could be the speed of one molecule, or the speed of a set of molecules, or the kinetic energy, the potential energy, whatever. This is an observable. And if you look just at observable, then things become objective in a very natural way. You can define an entropy for an observable for a given value. You can define a entropy function for an observable. So the entropy for this observable is going to be a function of A, and small a is the possible values that my observable can take on. For instance, if it is kinetic energy, it would be from 0 to infinity and so on. So, and what is this entropy? Is again the log of some volume, and this volume is the volume of states compatible with energy E and with the value small a of my observable. And this is what I call the entropy. Well, this is Einstein's definition of entropy, so it is nothing new. Actually, once you have this definition, and if you have some ergodic assumption, like the phase space is visited by the system in a uniform way, or sampled by the system in a uniform way, then you can easily derive that the probability that my observable capital A has the value small a is the number of what we learned in the high school, the number of favorable cases, which are these ones, divided by the number of total cases. So this is very simple. And if you write this in terms of the entropy, you get something called the Einstein formula. So this is nothing new. This is nothing new, but it's objective. There is no, you can define this for any observable, micro, macro, whatever. And there is no any, once you give me an observable, and I give you the entropy, and I give you the probability distribution of this. So this is completely objective, and it is related with experiments. If you run an experiment, and then you record the value of your observable, capital A, on time, and if you wait long enough, you get you plot the histogram of this data, and then you get precisely the Einstein formula. And this is this has here equilibrium, non-equilibrium is not important because you have to wait long enough to do it. So this is completely, as I said, this does not depend on the observer. Does not depend on if the observable is micro or macro or whatever. So with this is enough to explain irreversibility, and the explanation is going to be very simple. If my observable starts with an initial condition which is very far from the support of rho, then it will go back to this region. So let me call this the most likely value, A star, and this entropy, this value is the value that maximizes entropy. It would be like the equilibrium state, but we are not talking about states. We are just talking about observables and the value of the observable. So maybe for an observable, I can have a value A star, and for another observable, I can have another value. And I am not saying anything about how broad is this distribution. Of course, here, if you have a macroscopic observable, is something that is going to have a very narrow distribution, but I don't care. I don't care now. So, and this is completely objective. And now we can define irreversibility in an objective way. And what is the definition? As I said, if my initial condition, A0, is very far from this region, far in terms of the Boltzmann constant, then for sure, the evolution of this observable is going to be from A0, it will go to A, from A0 it will go to A star, or close to A star. And that's it. It's so simple that that it's just you start with a very rare fluctuation and then you go back to normal values. This is irreversibility, but it is objective. Here I'm not talking about any observer or if the observable is macroscopic or not. It's completely objective. It's not precise because here you see what means this much larger. Well, it means that your initial condition must be very rare. And what means rare here? Well, it's not precise. It's not a precise definition. Why? Well, because you always have fluctuations, and irreversibility is always going to be masked by fluctuations. We know this from the very beginning. We know that entropy can decrease. It's very likely that you get decreases of entropy of the order of the Boltzmann constant. So irreversibility is always going to be masked by fluctuations. So it is not a precise definition of irreversibility, but it is an objective definition of irreversibility. As I said, this is a footnote, just a footnote. But if you really believe in this and you try to think of the problem of irreversibility with these ideas, you find things that for me were surprising. Let's apply the definition to some observables. So here we have a gas like this one, and let's apply to the position of a molecule. Okay, it's very easy to calculate. Remember, this is the objective definition. You give me an observable, I calculate an integral, and I give you a function. This is easy to calculate. This is a constant function. So look at the condition for irreversibility. If this is constant, the condition can never be fulfilled. So the position of a particle can never exhibit an irreversible behavior in a gas. Okay. So you need, well, there are observables that will never exhibit irreversibility. But look.
When you say a gas, you mean an ideal gas?
Yeah, an ideal gas. To prove this rigorously, you need that the gas is ideal. If not,
It is not relevant.
okay. An ideal gas with a small perturbation that makes it different. But yeah, it's true that here you need this ergodicity always. Okay. But now go to the velocity of a molecule in a gas. So if you calculate the entropy, there is nothing especially relevant in this calculation. You get, and you apply the Einstein formula, you get the Maxwellian distribution. So this is basic statistical mechanics. But now let's apply the definition of, and now you can have irreversibility in the velocity of a single molecule. So if your molecule has a very high velocity, such that the kinetic energy is 100 kT, for sure you will get an irreversible behavior. So if the initial condition, the initial velocity of your particle is much bigger than kT, you will have a relaxation. You will have a relaxation. And it's a microscopic observable. And you can even imagine a situation, and this is the example that I always give. You have here my gas in equilibrium. Let's say that it is, imagine that it's in equilibrium, and a cosmic particle or whatever, it comes and hits a molecule. And this molecule acquires an energy which is 100 kT. So what you will have there is a situation where the macro is reversible, A macroscopic observable will not see any irreversibility, but a microscopic observable will see a relaxation to values of velocity which are close to kT, values of kinetic energy which are close to kT. So irreversibility has nothing to do with the scale. It has to do with the number of degrees of freedom. Of course, you need a large number of degrees of freedom to get this, because you need ergodicity, and for ergodicity, you need a large number of degrees of freedom. But the observables can exhibit irreversibility or reversibility according to the initial condition. It has to do with fluctuations, and we go back to one of Raul's and mine obsessions, which is fluctuations. The really important thing in irreversibility is fluctuations, but not the scale. Okay, I think I try to continue working on this definition of irreversibility. One possibility is if there is an objective definition of equilibrium. One could be tempted to say, what is a microstate, equilibrium microstate? One could say, one state where all observables cannot exhibit irreversibility. But if you do this, this fails because you can always construct irreversible observables, like this one. If, like, well, this is a bit technical, but it's not. I mean, it's not very hard to find it. That if you are in this microstate, this is my phase space, and you define an observable that it's 1 in this microstate and 0 elsewhere, so finally you will. Oh, I don't know why this. I'm so sorry. And I think this is mine as well. Because I have to. Okay. Okay, equilibrium fails. I just want to finish in 5 minutes. So if you define equilibrium as the state where all observables have a reversible behavior, then it's easy to see that this fails. Okay, and well, I want it to be short. So this is the story. This is, well, you see conclusions of first part because there is this talk has a second part, but I will just mention the second part and to finish. So to conclude, sometimes I'm very excited with all this, but I recognize that it is very that the new things is just a reinterpretation of Einstein formula and so on. But I think that I didn't give you an objective definition of entropy or objective formulation of statistical mechanics, but I did give you, I did locate where objectiveness and subjectiveness are in the formulation of statistical mechanics. And this is the last, well, the conclusion of, you see, what I've showed you is that you can define completely and in an objective way the entropy function of an observable. You give me an observable, the position of particle 5, and I construct the entropy function. I tell you if when this observable is going to have an irreversible behavior and so on. So all this is objective. And I can show a second law for these entropy functions that for most observables, I can show that the entropy increases. So this is completely objective. Where is the subjectiveness or arbitrariness in statistical mechanics? In the choice of observables. What Boltzmann did was actually, more or less, is to imagine what a macroscopic observer can have access to. And this is the choice of observables. You can, for instance, sometimes there are natural ways of choosing observables, like in the system in contact with a thermal bath, your observable is the microstate of the system and the average energy of the bath, and so on. And in kinetic theory, sometimes the observables are those which involve one particle or two particles, for instance, things like that. And then what it is also subjective is to talk about the entropy of a system. What is the entropy of a system? There is no, whenever, or at least from what I've done, is you cannot talk about the entropy of a system. You can talk about the entropy of an observable, or if you choose a set of observables that describe your system macroscopically, for instance, then you can talk about the entropy of a system corresponding to that choice of observables. Okay. So an equilibrium is something that I think we are not sure or I'm not sure if we can define it in an objective way or subjective way. So I will finish just to mention that an open question is how a system can generate giant fluctuations. So how can I mentioned this example of the cosmic ray hitting a particle, but in general, why we observe, why we have this irreversible behavior, for instance, that this falls here. So how can a system start with an initial condition which is very unlikely? By definition, things that are unlikely cannot be observed. And I have here the conventional answer is that the universe started in a very low entropic state, and this low entropy somehow has spread out in the universe. For me, this is not very convincing, so I have another explanation, but I will not give it to you here. This is a teaser. You can find it if you are interested. You can see this in my YouTube channel. There is a video with this the second part, which today we will have no time. So thank you very much.
Thank you. So we have time for one or two short questions.
I have two problems. Maybe better to discuss that over coffee. But one problem is that according to your strict definition, the system is out of equilibrium all the time.
Yeah, equilibrium is
now when it crosses the maximum is at equilibrium, then it's out of equilibrium. So you need some quantitative amount how far it has to be.
This this, as I said, one have to distinguish between imprecise and objective, or precise objective, imprecise subjective. So any definition of irreversibility is going to be imprecise. Any definition of irreversibility, because irreversibility is this
not
behavior.
If you restrict yourself to large systems.
Okay, but then you have the problem again. What is a large system? And the fluctuations will be 1 over square root of n. So at the end of the day, you have the same problem. What I'm trying to do is to avoid, in the formulation of the problem of irreversibility, avoid anything. When I said subjective, I mentioned something which is arbitrary, which is not in the object, in the nature. When you have to put something from outside, like largeness of large number of the system is macroscopic and so on.
So can you define irreversibility for a system with 3 particles? A gas?
No, because you need ergodicity. This is the point. So there is still. So when I said it's micro doesn't matter, I refer to the scale, but you need a uniform sampling of and for that you need a large number of degrees of freedom. Yeah, but then the times. Yeah, probably you can do some statistical mechanics with particles, but this is here I'm assuming this also is inspired more or less in stochastic thermodynamics. So here I'm assuming large number of degrees of freedoms, ergodicity. Of course, this is another problem. I mean, this is in statistical mechanics there are many fundamental problems. One is ergodicity. One is this objectiveness of irreversibility. There are many. I try to address only one. So I assume that the system is ergodic.
So my question is not also the state space a subjective thing? I mean, so
the phase space.
See, yeah, the number of.
Well, we think, no, I start with the assumption that Newtonian dynamics is objective, so position and velocities are, of course, if you go to quantum, I think you can translate this to quantum, but I assume that position and velocities are objective things that are there independently of what we think about them.
But I was more thinking like, for example, if you go to my room, so you will probably say that this is in a high entropic state. But But if you have access to my memory, probably you will see that it's not so disordered because you remember where all the things
But this is not here. This is this identification of entropy with disorder and so on. Here here it's only mechanics plus ergodicity and mechanics. And Einstein formula, which is a probabilistic, well, not even a probabilistic, because this is real things. This is a histogram of real data. Okay.
Thank you.
Yeah. So thank him again. We move forward, not backwards, as Raul wanted, with this rich program. But before we continue with the presential speakers, who for sure will enjoy the extreme hot weather and the extreme crowded beaches of Mallorca, before that, we have other non-presential contributions from researchers who could not come but didn't want to miss these celebration workshops. So let's start with the first of them.
Hola Raúl, quería felicitarte y desearte que cumplas muchos más y agradecerte todo lo que nos has enseñado a los que hemos tenido la suerte de ser alumnos tuyos. Aún recuerdo que cuando era estudiante de doctorado tenía unos apuntes manuscritos tuyos sobre la expansión de Van Kampen que yo guardaba como si fueran un tesoro, y los desarrollos matemáticos que hacíamos en la pizarra, que siempre eran muy estimulantes. Un saludo y a ver si nos vemos pronto.
Hola Raúl, siento mucho no estar ahí para tu 65 cumpleaños. Me hubiera gustado, pero no me ha sido posible. Así que lo menos que puedo hacer es mandarte este vídeo para desearte muchas felicidades y muchos éxitos en los 65 que te quedan por cumplir. Y nada, decirte que tú has sido una persona que me ha influido mucho en mi manera de hacer ciencia, de tomármela en serio, sobre todo con lo que he aprendido de ti a la hora de ser riguroso con los números. Tuvimos solo un paper juntos, que debería aparecer ahora la foto, pero bueno, fue un paper de que aprendí mucho y que creo que introdujimos un concepto que está muy poco explotado, que es el de las transiciones de fase aparentes. También es cierto que compartimos momentos intensos, como el workshop de nuestra escuela de doctorado en el Parador de Gredos, que recordarás que fue un gran éxito. Aquí habría que mencionar al amigo Parrondo también. Y por lo demás, hemos pasado muchos ratos muy buenos y espero que pasemos muchos más. Espero que como mínimo nos sigamos viendo en los FISES y haciendo las reuniones gastronómicas que hemos venido haciendo otras veces. Y nada, poco más que decir. Un beso para Toñi y que disfrutes del día. Nos vemos pronto.
Raúl, muchas felicidades. Aprovecho la ocasión para decirte que fue un gran placer coincidir contigo en el IFISC y haber podido colaborar contigo y haber aprendido tantísimo de tus trabajos. Aunque hayas cumplido los 65, espero que sigas mucho tiempo más tan activo como siempre. porque necesitamos de tu sabiduría. Un fuerte abrazo desde Barcelona.
Next speaker is Maxi San Miguel, researcher here at the FISC. Okay. Okay. So I thought that he wanted to talk about Fran Pereira's hit 1 más 1 son 7, but better we wait to understand what he's referring to.
This is not a scientific talk. This is a talk for Raúl, and I talk to Raúl in Spanish. Los que os aburráis, miráis el móvil. No conozco a Raúl desde el año 58, pero bueno, según él, yo ya le di clases de problemas de mecánica cuántica en Barcelona, cuando estábamos él y su director de tesis, Joaquín. Pero de hecho la relación fue más estrecha desde que él vino aquí en el año 89. Raúl y yo nos llevamos técnicamente un sexenio de diferencia y hemos siempre pedido los sexenios juntos. Yo pedía el n y él pedía el n-1. Pero la vida es no lineal, entonces satura, él tiene 7 sexenios, yo también tengo 7 sexenios, no podemos pedir más, pero tenemos uno de diferencia. Bien, ha sido un camino juntos, recorriéndolo largo, en el que yo siempre veo que ha habido 2 aspectos. Uno, que siempre hemos estado en muchas guerras en la misma trinchera, luchando mientras nos caían las bombas, pero que también ha habido muchos momentos en que nos lo hemos pasado muy bien y de ocio, diversión y disfrutar la ciencia. Quiero dar simplemente 2 ejemplos de estos 2 aspectos. El primero de ellos, el Raúl fiel a sí mismo, que se cabrea y dice esto no puede ser. Esto es año 2003, nos están intentando echar del IMEDEA. Raúl sabía que no había agua en la piscina, pero se tiró a la piscina y se presentó como director. Obviamente no salió, pero muchos lo agradecimos siempre. Esta es una de las formas de ser de Raúl. La otra es el Raúl fiestero, el Raúl simpático y amable, y qué serían los solsticios del IFISC sin la paella de Raúl. Bien, lo que yo quiero hacer ahora es recordarle a Raúl las cosas que hemos hecho juntos. Y lo sé porque a cierta edad, y lo digo por experiencia, uno se olvida de las cosas que ha hecho. Entonces, se lo quiero recordar. Y yo mismo me sorprendí cuando conté que hemos escrito 37 papers. Sí, ya te digo que tú tampoco lo sabías. Y que además una manera de hacer la ciencia que yo he disfrutado con él es que esos 37 papers tienen 22 coautores distintos. Esto es solo una pequeña parte de las contribuciones científicas de Raúl, pero es la que yo he disfrutado y la que yo quiero contar aquí. Yo lo he dividido en varias etapas cronológicas. En cuanto él llegó aquí, pues empezamos, bueno, pues lo que estábamos haciendo entonces, láser, óptica cuántica, squeezing y este tipo de cosas. Y esto, Emilio también colaboró en estos trabajos, he puesto aquí uno en el que estaba Pera. Pero además lo que pasó en aquella época fue importante, porque mientras hacíamos estas cosas esotéricas de los squeezing, redactábamos una propuesta de creación de una unidad estructural de física de sistemas complejos en el año 1990. Y eso fue el principio de la historia. Raúl participó en ello y luego Raúl fue investigador científico del CSIC en lo que era el Instituto de Estudios Avanzados, como os ha emocionado. Siguiente etapa era formación de estructuras. Y ahí tengo aquí un ejemplo. Aquí la pregunta era, cuando hay una inestabilidad y se forma una estructura, ¿el número de ondas seleccionado es el que es más inestable o el que minimiza el funcional de Lyapunov del problema? Al menos la pregunta la teníamos bien definida. No teníamos PowerPoint, hacíamos este tipo de transparencias así. Tampoco había índices H y cosas de estas. Entonces, en los agradecimientos, pues se ponía que nos lo habíamos pasado muy bien en la colonia San Jordi y esto aparecía en Physical Review y nadie protestaba. Además, como ha mencionado Raúl, este señor, Jorge Viñals, tiene algo importante en Raúl viniendo aquí. Raúl ha mencionado, si no, no lo hubiera dicho, que vino a una plaza que no era para él. Esa plaza era para Jorge Viñals. Pero Jorge Viñals me llamó y me dijo, Maxi, no lo entienden, no lo quieren entender. Yo me quedo en Estados Unidos, no voy a ir allí. Si yo fuera tú, buscaría a alguien que quisiera ir allí. Bien, pues yo llamé a Raúl. Los señores locales del Tribunal de la Plaza la querían dejar desierta. Suerte que había un señor de Madrid, un externo, como siempre, Antonio Hernando, que dijo que por encima de su cadáver se dejaba aquella plaza desierta con el currículum de Raúl. Y gracias a eso Raúl está aquí. Bien, después de eso, bueno, pues en unos años fuimos haciendo cosas. He querido sacar aquí esta foto porque es fin de una época, 25 años de mecánica estadística de no equilibrio en Sitges. Aquí, no sé por qué no se ve, pero está Joaquín, el director de tesis, está Raúl, estoy yo, está Horacio, está alguien que a todos nos hubiera gustado que pudiera estar hoy aquí, que es Chris Van den Broek. Pedro Garrido está en la lista de asistentes, yo no lo he logrado reconocer, debía estar muy joven. ¿Estás? Bueno, pues, y Juanma creo que no estaba, pero estuvo presente, porque allí se presentó ese paper tan fundamental de Raúl, Chris y Juan. Bien, luego también fue en esa época cuando empezamos a ir mucho a Chile, y empezamos a ir juntos, y en el año 95 dimos un curso sobre procesos estocásticos. Yo recuerdo perfectamente a la 1 de la madrugada en la terminal del aeropuerto de Barajas escribiendo las transparencias diciendo no, que esto no es así, que no sé qué. Bueno, y luego escribimos este paper donde Raúl enseñaba, hombre, es que no saben ni simular una ecuación lineal con ruido multiplicativo, etcétera. Este artículo se sigue citando y se sigue citando mucho desde el punto de vista pedagógico. Seguimos yendo a Chile y esta no está aquí, bueno, es igual. Esto es con Horacio, como se ve por la calva de Raúl, habían pasado unos cuantos años, pero la leyenda dice que en este viaje con Horacio los tres nos limpiamos el aura en un valle de Chile. Supongo que tenemos que volver, que la debemos tener un poquito guarra. Sigamos. Siguiente etapa. 98-2001, segunda etapa de formación de patents. Esto fue esencialmente la tesis de Rafa Gallego, ahora que fue codirigida, nuestra primera tesis codirigida. Aquí pues era la época en que nos emocionábamos haciendo peliculitas y cosas de cómo aparecían estas estructuras espaciales, del modelo este modelo de 3 estados con las espirales. Aquí también participó Daniel Valgraev en estas, la religión entonces era la ecuación de Ginsburg-Landau compleja y cómo aparecían distintas fases, etcétera. Seguimos, nos empezamos a ver la verdad, empezamos a ver la dinámica cultural. Entonces, en esta época, 2003-2005, escribimos 5 papers con Konstantin, que estaba escuchando, y con Víctor. Este paper es uno de los top 3 de Raúl, y su contribución fue muy importante porque volvía a las noise-induced transitions que había hecho con Chris y con Juanma. Y bueno, lo que veíamos es, bueno, no iba a hablar de ciencia, el efecto de lo que se llamaba cultural drift, que no es nada más que ruido en la existencia no de una transición. Y bueno, también empezamos a ver cosas de formación de opinión. De nuevo, este paper era con Horacio y con 2 estudiantes de doctorado de Raúl, Pau y Claudio, basado en ideas de este prohombre de la sociofísica, que es Serge Galam, que dio como yo, definición de existencia, porque aquí pone en francés un sociofísico. Esto aparecía en un periódico que se llama Serio, Le Monde, en el año 2005, por tanto la sociofísica existía. Y Y luego viene la época dorada. La época dorada 2013-2022 en temas sociales, en la que hemos escrito 17 papers juntos, lo cual quiere decir del orden de 2 papers al año juntos. Para mí esto es remarcable porque a su edad y la mía, y dentro de la clase de universalidad del comportamiento universitario y académico, estando los dos en la misma institución, lo normal es que estuviéramos peleados. Y como mucho que nos ignoráramos. En vez de eso es cuando hemos colaborado más juntos. Y bueno, esto empezó con la segunda tesis conjunta dirigida por Raúl y por mí, de Adrián Carro, que vino de hacer un máster en París y ahora está trabajando en el Banco de España. Y aquí yo ya le empezaba a estirar a Raúl hacia la verdad definitiva, que es el modelo del votante. Entonces estudiábamos el modelo del votante en redes complejas, he dicho que no voy a hablar de ciencia, también con algunas excursiones en temas financieros, había datos, bien, fue esto una tesis memorable de Adrián. Y después de eso ya fue 2016-2022, en esta época dorada, hemos trabajado con José, colega nuestro, con 4 postdocs distintos, Aga, Nagi, Megdat y Cristos, y con 2 estudiantes de doctorado, Oriol, los directores oficiales éramos José y yo, y el director de Raúl Stoni, que ha aparecido, el director de Tony Raúl, que ha aparecido antes, y hemos hecho muchas cosas juntos. Quizás, bueno, pues un punto destacado de todo ello es el número especial que editamos entre Raúl y yo de sistemas sociales. Claro, he de seleccionar algún artículo de esta época, y el que he seleccionado es este de aquí, Aging Induced Continuous Phase Transition, y a mí me gusta porque es un totum revolutum. Estamos gente senior, Raúl, José y yo, Oriol, que era estudiante de José y mío, Tony, que era estudiante de Raúl, y después de ese artículo han salido varios otros artículos por autores de estos y de otra gente, cosas en las que ha trabajado Tobías, otras cosas que ha hecho Raúl con Nagi y con Tony, o sea que fue, bueno, un poco esa manera de hacer ciencia, hagamos una cosa juntos y luego se puede ir explotando de distintas maneras. Aquí quería explicar un poco de ciencia, pero como los organizadores cortaron mi charla a la mitad de lo que me dijeron al principio, os quedáis sin ciencia. Ahora, no obstante, sí un poco qué es esto de aging. Esta es una transparencia de David, que está allí, que yo he retocado oportunamente. ¿Qué es esto de aging? Es, the longer you are in a given state, the longer your persistence time, the smaller is your probability to update. Entonces, ¿cuándo cambiamos de lenguaje de programación? Aquí hay muchos estudiantes que conocen a Raúl, y cuando le van con ciertas ideas, Raúl se pone serio, casi como en las trincheras, y dice Fortran, Fortran, Fortran. Bueno, aunque luego me pasa vídeos de cómo usar ChatGPT. O sea, pero... entonces, bueno, eso es la idea, de que si has estado utilizando algo durante mucho tiempo, te va a costar cambiar de estado. Entonces, entonces, bueno, pues muy rápidamente, el llamado Noisy Voter Model, pues tiene una transición de fase de las que les gustaban a Juanma, a Cris y a Raúl. Es una transición de fase en que la distribución de probabilidad va de 2 picos a un solo pico, es inducida por ruido, es discontinua, pero no es una transición de fase porque desaparece en el límite termodinámico. Bueno, resulta que si uno pone aging, la transición en vez de ser discontinua pasa a ser continua, pero es que es mejor, se convierte en una transición de fase honesta a los ojos de los dioses de la mecánica estadística. Es una transición de fase que pertenece a la clase de universalidad de Ising, y esto se puede demostrar y ver exactamente lo que es. Y además se puede entender en términos de una rotura de simetría, en que al principio hay 2 estados equivalentes, 2 grupos equivalentes, entonces unos se hacen más viejos que los otros y aparece una transición de fase. Más o menos creo que estamos at the age of this en el IFIS, que es una transición de fase entre 2 grupos de edades distintas. Bien, Aparte de esto, hemos hecho otras cosas interesantes con Raúl. Esto es la conferencia Solvay en Bruselas, en que los dos estábamos invitados en el año 2016, con nuestro gran amigo Lutz Szymanski-Geyer, que es otra de las dos personas o más que ya no nos pueden acompañar. Aquí, en una conferencia de sistemas complejos, vimos a ver si entendíamos la complejidad de las pirámides en México. Pero aparte de pasarlo bien, también hemos hecho trabajo experimental. Y Raúl y yo nos fuimos de trabajo de campo en Malasia, en el año 2019, a ver eso de la sincronización de las luciérnagas. Veis que aparece la sincronización y tal. Entonces yo tengo esta película en la que... No sé si se ve nada, pero es que tampoco vimos nada, ¿eh? Bueno, hay una película ahí que de vez en cuando sale algo, de vez en cuando sale una cosa así, que yo nunca sabía si eran luciérnagos o un faro de un coche que pasara por allí. Pero bueno, vimos que lo de la experimentación era difícil y vimos la sincronización de las luciérnagas. Bien, me dijeron que sea breve, soy breve. Outlook. Outlook quiere decir Raúl looking out. Entonces, es lo que estaba haciendo ahí. Raúl hace años me regaló este chiste, que es apropiado quizás para el domingo, ¿no? No os molestéis en votar, gobierna un algoritmo. Entonces la pregunta es si queda espacio, queda algo para hacer, pues para personas, creo, como yo y como Raúl, que nos gusta pensar, nos gusta preguntar, o sea, ¿qué podemos hacer todavía? Bueno, pues doy 3 cosas que vamos a hacer. Una, dentro de una semana nos vamos a Tokio. Nos vamos a StatFis. Este es el último StatFis en Buenos Aires, donde Raúl estaba dando una charla invitada. Ahora Raúl es miembro de la comisión C3 de la UPAD, de Física Estadística, donde me ha reemplazado. O sea que de alguna manera seguimos ahí juntos. Y después de 2 tesis codirigidas, vamos a dirigir una tercera tesis. La tesis de Jaume Llabrés, que hoy no está aquí porque es parte de esta expedición del IFISC a la India, que se han ido 10 o 12 o no sé qué. Entonces hemos empezado a codirigir esta tesis y bueno, pues me vienen y me enseñan esta cosa de aquí, que es un ejemplo de lo que él ha llamado Keep It Simple. Para los que no sepáis, se ha olvidado una letra, el lema del ejército americano, KISS. Keep it simple, stupid. Bueno, pues esto es lo que me enseñan como una cosa simple, me vienen ahí y tal, yo me pongo nervioso, entonces digo, bueno, pero esto va como la exponencial o como el logaritmo. Entonces nos jugamos unas cervezas, al final las gané yo y claro, quien ha de pagar es el estudiante que vino con las cervezas a la siguiente reunión, o sea que nos lo seguimos pasando muy bien. Raúl lo ha mencionado, y como sé que además está allí, lo ha mencionado en su primer speech, la vida de Raúl y la vida científica hubiera sido distinta sin Toñi. Por tanto, mi homenaje también a Toñi, que está allí. Y termino, pero con una gran primicia informativa. La última respuesta. Todo lo que queráis saber y no sepáis sobre el modelo del votante lo encontraréis en un review que Raúl y yo vamos a escribir cuando nos cansemos. Y además Fede nos ha dicho que nos va a ayudar y por tanto esto será la última respuesta al tema. Nada, termino. Raúl ha terminado diciendo "The best is yet to come". No es que yo supiera lo que iba a decir, es que con el café he podido entonces, hombre, por el sexenio de diferencia, pues no lo sé, tendría mis dudas de si the best is yet to come, pero si no ne vero, è ben trovato. Felicidades, Raúl. Si hay preguntas, serán sobre cosas que solo puedo responder después del segundo gin tonic. O sea que...
Yo tengo una, Maxi. Maxi.
Ha sido una gran primicia informativa. Bueno, he de decir que Raúl me ha presionado sobre eso durante varios años. Yo le he dicho que, bueno, para la jubilación.
¿Escucháis a los de Zoom? Maxi, ¿me escuchas?
¿Sí?
Hola Maxi, hola, buenos días Raúl, feliz cumpleaños. Solo quería aparecer para decirte muchas felicidades. ¿Me
Perdón,
oís?
no sé si te reconozco.
Llamo desde Minnesota, Jorge.
¡Hombre!
Hombre, Jorge, muchas gracias por estar aquí.
Feliz cumpleaños, Raúl. Solo tengo una pregunta o una cuestión, como diría Maxi. ¿Por qué hacéis esto tan temprano? Un abrazo,
Soy más pájaro
Raúl.
nocturno siempre, ya lo sabes, ¿eh?
Bueno, gracias, Jorge, por estar aquí. Es que más tarde hace un calor que se cuece
Oye,
aquí y todo.
gracias por no venir a la plaza, ¿eh? Hace 30 y tantos años.
Un abrazo para todos.
Muy bien.
Gracias, Jorge.
So, gracias, Maxi. So let's continue with another set of videos of contributors that couldn't come.
Muchas felicidades, Raúl. Siento no poder acompañarte hoy, me hubiera encantado. Espero que lo estéis pasando muy bien todos juntos. Quería darte las gracias por todo lo que nos has enseñado y lo que nos tendrás que seguir enseñando. Venga, un abrazo y que lo paséis muy bien. Hasta pronto.
Mi nombre es Miguel Pineda. Hice una estadía postdoctoral con Raúl en el IFISC. Apreciado Raúl, felicitaciones por tu cumpleaños. Y de Raúl recuerdo muchas cosas. Recuerdo su intensidad y su vitalidad para aportar temas científicos. También recuerdo que aprendí mucho durante mi estadía, durante casi 2 años que estuve en el IFISC como postdoc. También tengo varias anécdotas y una de las anécdotas muy interesantes que recuerdo es que durante mi estadía en el IFISC, Raúl tuvo un accidente o una especie de caída en bicicleta y estuvo un poco enfermo por un tiempo, así que hubo una especie de interrupción del proyecto que estábamos trabajando. Recuerdo que era un proyecto de formación de opinión continua. Y un día alguien que lo fue a visitar me contó, llegó al IFISC y me contó, no, él está recuperándose y lo encontré trabajando en el proyecto que ustedes están trabajando. Y luego de eso, cuando regresó al instituto, él todavía seguía un poco convaleciente, no podía caminar un poco muy bien. Y bueno, uno podría pensar que, bueno, si Raúl estaba en esas condiciones, una vez que regresó, pues bueno, cada vez que uno tenía reuniones con él o había una reunión en la que él tenía que participar, pues se podía hacer en su oficina. Pero resulta que no. Resulta que Raúl andaba en la silla de la oficina, de un lugar a otro, yendo de una reunión a otra, y uno lo veía en ese plan. ¿Okay? Eso quiere decir mucho sobre Raúl, sobre su pasión por el trabajo, sobre su compromiso y sobre su vitalidad. Pues feliz cumpleaños, Raúl. Espero que cumplas muchos más con esa vitalidad y esa fuerza que siempre te ha caracterizado. Y espero que nos podamos ver pronto. Saludos y muchos abrazos.
So, thank you for all of them. Next speaker is also an IFIS researcher, is Horacio Huillo.
Well, first of all, it's a pleasure to be here to celebrate Raul's 65th birthday. And we talk today about some results we have obtained in relation with the Carter-Bracey-Sank growth model. It's something in which we have not collaborated with Raul, but we have discussed, and he has worked. Yeah. So, just to make a short remembrance, I met Raul for first time more than 30 years ago here in Mallorca, in '89, I think. And we started our collaboration a few years later. So it's almost 30 years of collaborating, not 30 papers, but several. And during this time we have met in several conferences. As Maxi had said, we coincide in several cases in Chile, in Valparaiso, and we have enjoyed seafood and good wine. So let's go to the subject. The Carter-Bracey-Sank equation is an improvement, let's say, over the Edward equation, including the effects of curvature. And it was introduced in the middle 80s. And for a long time, people has insisted in because they were not able to find a functional describing to derive the equation, that it was a real kinetic equation describing a non-equilibrium process. We have shown that it's not true. It's possible to write the equation as a gradient expression, and that this functional, that according to Graham is a non-equilibrium potential. He said that I am allowed to call it non-equilibrium potential. Even Raul says no. And the form is this thing here, that is little, with an integral term, it's a little complicated. This functional has this property, but it's not a Lyapunov functional, because if you project this this quantity in some plane, you will find that this a cubic-like functional. So it's not bounded from above or from below. Just in discussions with Raul, with Emilio, and with Pera, some visit that I did several years ago, we have found that instead of writing this complicated functional integral here, it's possible to write in this way. And this makes the things more easy to understand, in the sense that we have that this term implies that there is a long memory. This is something that has been proved recently by diverse methods. People like Irwin, Heider, etc., have shown that through different transformation processes, it's possible to show that the final distribution is a Tracy-Whedon distribution. This is not seen here, but what is seen here is the origin of the memory. We have analyzed the behavior, the time behavior of this distribution, of this functional, sorry, and have found that, for instance, for the Edward Wilkinson case, that means lambda equals 0, we have a growth until some plateau is reached. And after turn off the lambda contribution, the nonlinear contribution, we have that there is a bending of the curve, and there is a linear behavior. This is in 1, 2, and 3 dimensions, so it's independent of the dimension. And there are two characteristics. One is the slope here is linear, behaves linear with a coefficient, linear t with a coefficient proportional to lambda square. And the bending of the curve signals a time in which we have a crossover from the linear to the nonlinear behavior. So the Edward Wilkinson behavior to the Kapizet behavior. And this was shown by a lot of simulations. Unfortunately, it's not easy to do analytical things. And sorry. And here we have a plot of the slope in terms of lambda. This is logarithmic. And we have, it's really linear most of the time. And this is the time at which we find the maximum of the curve. That is the crossover time, or some characterization of the crossover time. Another thing that we have also studied is the effect of memory. Starting with this initial condition, that is a kind of linear well, we can see that for a fixed lambda and working in 1 and 2 dimensions is the same, we find that depending on the value of A, that is the initial slope, the response of the behavior of time behavior of the functional is different. So the system keeps memory of the initial condition. Of course, in this finite case, we are making the simulations in a finite system with periodic boundary conditions. And at some moment, the correlation length is similar to the size of the system, and in this moment, things break down. We have also analyzed, look at the possibility of making stochastic thermodynamics with the Kapizet case. This was started several years ago, in 2010, by Barato, Chetrit, Hendrickson, and Mukamed, but doing simulations in a model, the position model that belongs to the Kapizet case. On one hand, Dickegam and Seifert analyzed the possibility to find a thermodynamic uncertainty relation, doing some renormalization group calculations in the Kapizet, while with Miguel Rodriguez we analyzed the stochastic entropies and the numerical proof, let's say, of fluctuation theorems in this system. After that, we have make an analytical description of the way in which we can obtain the entropy of a trajectory and prove different fluctuation theorems. And finally, in this paper with Rafael Gallego, who has worked with Raúl, we have analyzed the separation of internal and external or collective contributions and proved fluctuation theorems for both set of variables. In order to show how it's possible to derive in terms of the functional, the entropy production, this is the probability of, for a given trajectory, it's in terms of the action is the integral of the Lagrangian that is written here. The Lagrange has a Onsager-Markov form, and we can reach a detailed fluctuation theorem just looking at the difference of the actions for the forward probability and the backward probability. So going through the same trajectory forward and backward, and obtaining the ratio between the probability of the forward and the probability of the backward trajectories. We can express this in terms of the exponential of the difference of the functional, and this is the energy production. So this functional is not a free energy, but an entropy like functional. It is also possible, after some manipulations, to show a Crookes-like relation in which the probability of the forward process is related with the probability of the backward process. And we have also proved some integral fluctuation theorems. Regarding critical exponent, this is an important point in the sense that what people try to define, to determine. So what we have done is separate the coordinate, that is the height function of the height, with the mean value and fluctuations around this mean value. The mean value is defined in this way, and one important point is that the integral in the system, the integral of the system of these fluctuations gives 0. That indicates that the system is overdetermined, and we must take care when doing analytical calculations or numerical calculations. Using this separation and also this very well-known family Bichik scaling, that implies that we have the collective motion and the behavioral fluctuations, and this coordinate for this fluctuation function is related with our coordinate in this way. We introduce this into the functional. But to do that, we use these relations between the gradient and the time derivative of the fields, and separate the functional in 3 contributions. These 3 contributions that are here, and introducing the family Bichik scaling, we can obtain conditions, some certain relations, like here for the second term, in which we see that after introducing the scaling here, we get something that is a number times exponential of the time. And this exponential of time relates the growth exponent and another of the classical exponents. So plotting this, the logarithm of this function, the slope, plotting this, the logarithm of this function in versus log of t, where we find a slope, a line that has a slope that relates beta with zeta. Beta, zeta, and alpha, the 3 critical exponents, are related by several 2 relations, but not for 3. This introduces a third condition, or it's assumed that it will introduce a third condition and can be allowed to determine these exponents. An alternative way is to work not with the functional, but with the time derivative of the functional, in which the process is easy to see because it will relax to 0. As I said at the beginning, the time behavior of the functional is linear with t, so it would reach the time derivative of t would go to a constant. Another interesting point is that through the Fokker-Planck equation, we can look for the probability distribution function. One thing that is we interpret, we just, let's say, at the beginning is that there is no stationary solution. However, one possibility to look at the probability distribution function at long times is to solve a Fokker-Planck equation, which is not an easy task because it's the infinite dimensional, in principle, infinite dimensional equation. But it's possible to think in, given certain initial conditions, to use a short time propagator that has this form that is expressed in detail in this way, and it's a function of the functional, and to exploit it somehow. It's still a work in progress to see how it's possible to get results, really. But we can say something that the people have thought for a long time. This distribution here is the probability, the equilibrium probability distribution of the Edwards-Wilkinson case. This is the functional for the Edwards-Wilkinson. And people thought that it was also a stationary solution of the KPZ case. However, if you propagate with the short time propagator this distribution, you will find that in the short time t tau, the probability, the functional change. So it is not stable. It's a stationary point, unstable stationary point. Okay, that's to conclude. We can extend this. I think I was too fast. It is possible to exploit this kind of approach to study other systems. Like this one is also applied in here. It's the original paper by Golubik and Wisner, in which they introduced this equation to describe growth process. And with this nonlinearity here that corresponds to the Müller-Sekerka model that it was used to describe the Müller-Sekerka instability in directional solidification. This, as a matter of fact, in the initial study, we have obtained a functional that from which it is possible to derive the KPZ equation. And if we write this as an integral functional, introducing arbitrarily a non-local kernel, and a local kernel with a very limited a very short range, it's possible to think in expanding this non-local kernel in powers of the range. And at different orders obtained, order 0, Edwards-Wilkinson, the first order is KPZ, and the following orders gives several equations that have been used in this field. One of them is this. And it is possible to easily see that the equations can be written in this way as a derivative of a function, a gradient of a functional, and the functional has this aspect. It's similar to the KPZ one, and just looking at this form, we can say a few things. One, there will be some crossover from a linear behavior until a non-linear behavior dominates. And at long times, when the non-linear term dominates, the functional will decay linearly with time, because the form of this non-linear term is exactly the same as before. Also, because it has this structure, there will be memory. Eventually, something that we want to study. One thing that is not possible to say nothing is what happens with the critical exponents. This should be studied. But probably the critical exponent will be different because the linear term so has a different kinetic behavior. And well, just to resume, we have found that a functional description of the capacitic equation, which is valid for any dimension and the number of dimensions, it's possible to make an stochastic thermodynamic description of the process and to prove known fluctuation terms, eventually through some naive procedures obtain a thermodynamic uncertain relation. We have proven one dimension fluctuation theorems numerically, and it's possible to do this in more dimensions, of course. We are looking for the obtention of the critical exponents, is work in progress, as well as the obtention of the capacity hyphen probability distribution function. And we are testing some limit results. So presently, some people like Mirson and collaborators have shown some large deviation behavior in the short and long times of the capacity equation, and well, and so on. And that's all. Thank you very much, and happy.
Thank you, Horacio. We have time for a couple of questions, if any.
You mentioned that the potential decreases with time.
Yes.
But you show a figure in which there were some dots that decreased with time. There was a theoretical line, something that looked like a line, that first increased and then decreased.
Yes. Mm-hmm.
So what is the line that first increases and then decreases?
The increasing line corresponds to the Edward-Wilkinson behavior. Okay. The Edward-Wilkinson behavior grows and reaches a plateau.
Okay.
So after the nonlinear contribution wins, let's say, overcomes the contribution of the linear contribution, the line bends and goes down linearly.
Mm-hmm. So it only decreases because of the nonlinear term?
Yes, yes.
Hi, this is a slightly off-topic question, but I am surprised of the variety of people that has addressed the capacity equation, from statistical physicists, from Zhang. Your approach is in this area. There are also some experimental checks, but there are lots of pure mathematics of the capacity. Even the Martin Heyer won the Fields Medal working on topics related. Can you say something? Why is so important mathematically this equation? Do you have any idea?
Well,
I don't know if you have an answer or not.
My feeling is that it is a singular equation. It's very, let's say, like the equation, the Schrödinger equation. When you goes from the classical to the quantum realm, h bar makes a difference. It's not. You need to introduce some singular perturbation, let's say, the schemes. For instance, the WKB is one form. And I think from the mathematical point of view, this is the interest. From our point of view of physicists, it is an equation that describes a non-equilibrium system, an extended non-equilibrium system. But from a mathematical point of view, this is so far what I understand.
So thank you, Horacio, again.
Thank you.
The last set of videos of non-presential contributions.
Hola Raúl, con este vídeo quiero agradecerte lo bien que me acogiste cuando yo tenía tanto que aprender y también agradecerte mucho la energía, tu motivación, tu creatividad y tu rapidez, que siempre me han maravillado. Muchas felicidades y un fuerte abrazo.
Hola, Raül. Enhorabona pels 65 anys. Aviat farà 30 anys que ens coneixem i el temps passa molt aviat, tal volta, massa i tot. No voldria deixar passar l'ocasió d'aquest vídeo que et fan a l'IFISC per donar-te les gràcies per totes les teves ensenyances tant al grau com durant el doctorat. Sempre he considerat que has estat un dels millors professors que he tingut. Gràcies també per haver-me acceptat com a part del teu equip docent en moltes de les teves assignatures i haver-me donat l'oportunitat de continuar aprenent al teu costat. Sempre et tinc present com a referent a l'hora d'impartir docència. Val a dir que el llistó l'has deixat molt alt, no sé si mai hi arribaré, però vaja, a poc, menys si amb el temps ho aconseguim. Quasi 30 anys donen per molt, però ens han demanat que el vídeo fos breu. Així doncs, una vegada més, enhorabona, Raül. I espero que en aquesta universitat puguem seguir comptant amb la teva experiència i el teu saber fer per molts d'anys. De tot cor, moltes gràcies per tot, Raül.
Yeah, so thank you for all of them. Next speaker is Wojciech Korneta from Academia Lomstinka in Poland, who will talk about the chaotic electronic circuits.
The slide here, the slide. Oh, here. Yeah, you put this way. This is the presentation? Oh, no, the first slide. Where is the first slide? With title. Yeah, this one. Oh man, this is the first. Well, nothing. Okay. Okay. Good afternoon, dear Raul, dear friends. It's a big pleasure and honor for me to be at this event, at this 65 years celebration. And what can I say? I would like to thank the organizers for informing me about this event and for inviting me to be here and to have this small presentation. Small because they told me that I have only 5 minutes. 5 minutes, no more than that. Initially, I was not in the program, but now I got 5 minutes. So more or less, dear participants, during these 5 minutes, according to suggestions of organizers, a part will be scientific and a part will be personal, directed to Raul. When I come here about 20 years ago, more than 20 years ago, to cooperate with Raul, he suggested, at that time it was a very hot topic, stochastic resonance. This phenomenon, a lot of papers were in these most prestigious journals about this phenomenon. And in parallel, as you know, the end of 20th century, a lot of interest was devoted to chaotic systems. So Raul suggested, why not to look at the both effects, the stochastic resonance and the electronic circuits, which can have the dynamic chaotic behavior. He suggested this, and he even showed me some papers. I started to look, and we started to cooperate for a few years in this field. And one of the papers, which you can see here, is has got a lot of citation after this, because it connected these two effects, the
the stochastic resonance and the Chua circuit. Chua circuit, that's probably you know, is the paradigm of how this circuit was the first electronic circuit which shows the chaos. It was proven experimentally, also numerically and mathematically, that it shows the chaotic behavior. And in fact, we started to cooperate. This paper was so popular because there was for stochastic resonance the controversy that sometimes when we determine the optimal level of noise, the optimal level of noise was determined from Fourier transform. And the other method was to use the residence time when the system is one or the other state. And the level of noise was not correctly the same, not exactly the same for these two methods. And just we proposed in this paper how exactly how to proceed with the experimental data to get the correspondence of this. After this several years of cooperation with Raul, I moved to engineering department. I started to cooperate with professors of engineering department because I was more interested in application of this chaotic system and these events. And from this moment, many papers appear how to apply this Chua circuit to detect different signals. The electrical signals, and which are constant, which are changing in time, and also recently the magnetic systems. And the magnetic systems, because magnetic field is everyone wants to look how to detect even small magnetic systems, attracted a lot of attention. As I can see, we have had a paper with Professor Chua. Professor Chua was the developed this circuit, so you can see that this is the paper which we perform all these experiments we perform here. And Professor Rodrigo Picos from engineering department is the person which is permanently here. I'm coming for a short time, as you can see. This is as you can see how this magnetic stochastic resonance effect we detected. We have a big coil inside the small coil of Chua circuit, and it was possible to detect very, very, very low magnetic signals, of course, using these two methods after analyzing first by using the Fourier transform, and the second using the residence time. And this paper just got also a lot of citations because of the magnetic field, I think. The last what I want to show you, I think this paper appeared just in this year. This year, at the end of January 23, it's that we discovered the hysteresis effect. Hysteresis in this Chua effect, as you can see, also the Professor Chua is one of our cooperators. This is the effect which we first show that there is a hysteresis possible to open, because we want to find some applications. And the hysteresis is like this, that shortly about the Chua effect. These are from experiment. The two photos, as you can see, we operated in the single scroll, where there are two scrolls of there are two attractors. They are called the single scroll attractors. And after we started to apply electrical signal, triangular electrical signal, for very, very small frequency, we observed the following hysteresis effect. As you can see here, we started from 0. I will show you a short movie. It's about 100 seconds, so this is very, very, very small how it changes. So the single scroll decreases, and suddenly, boom, it goes and changes to the regular form. And after, of course, there are many bifurcations. But when you go back, when you decrease the voltage, it does not go like here. You can see this effect here. Again, you have boom and changes. This effect generally calls the chaotic hysteresis. What is chaotic hysteresis? Two effects act together. First is the hysteresis, and the other,
the system has chaotic behavior. When the two effects are together in one of the states, we can say that we are observe this. This is the new phenomenon called the chaotic hysteresis, observed also in turbulent and other systems. But this is in the paradigm in this system, in this Chua circuit, discovered by Professor Chua. So this here we operated in this single scroll regime. But even more interested was when, because there is a double scroll regime. If we go just close to because there is a from single scroll to double scroll regime. If we stop very close to the single scroll regime, but we are in the double scroll regime, you can see here is the effect of there is a double scroll, and after we can have one hysteresis at the right, one hysteresis at the left. We call this effect double hysteresis. And this paper, as I show you, you can read exactly about this new phenomena appeared, and it already has 3 citations because everyone is looking for application of this effect. So more or less now I would like to show the hysteresis, how it looks. When we change the triangular signal, it will last about 100 seconds, but I need the help how to, if you can put the movie wait 100, because I have 5 minutes. So, so I try to do it. You can see we start from the single scroll, and we change the voltage. The chaotic attractor starts to decrease. We change the voltage, as you can see, and suddenly in a chaotic hysteresis, boom! You see this changes suddenly, and when we increase, you have a lot of bifurcations, a lot of behavior. Finally, finishes like this. These are the whole system of all the different behaviors. That's why this system is so interested, and is still worth of studying and working. As you can see, we are now going back. But we must go to the negative voltage, because this is a triangular voltage. And suddenly, as you can see, we are 0 and now negative. We are going back to the negative voltage as this look. And now, boom, again, you can see there is so we have the hysteresis effect. You can observe this and describe, and here, boom. And again, going to the negative and going, we finish the movie at so we are going back to 0. So we started from 0, 100 seconds. So this is, of course, if the signal is faster, the hysteresis disappear. Only very small step by step, or very small. I mean, below 100 seconds the period. So we finish like this. I don't know how to stop this. No, maybe stop. So this was the scientific part, and now the personal part. For the first years of cooperation, Raul came to Poland to visit me, and he came just his son was born. He came with a travel bed and travel trolley for this child, and of course I invited him to Polish Sea Baltic. And we went to the Baltic, but even one time, Raul, and he was with wife and with his small son, even one time he didn't want to enter the Baltic Sea. Even when I insist, look, 18 degrees or 19 degrees, or sometimes in the maximum 20 degrees, are comforted to go to the sea, but even one time he didn't try to try our Baltic Sea. But funny thing was like this, look, in the pension he was registered, and he said, I am from Palma de Mallorca. When she heard this, impossible. So our sea is so attractive that now people from Mallorca come into Poland to Baltic Sea. And we are all laughing. And my pension, that person from Mallorca to go to my pension to stay. So it was a lot of thought, Raul, as you remember, it was and I think you enjoy this time and the travel, and you see. Now I officially want to invite you, because we have south of Poland, and in south there beautiful mountains. I invite you, now you have more rest. I invite you with family, with your son, which of course is now a grown person, to just to walk a little and to enjoy skiing, or we can enjoy the time like before. So Raul, I think the best, the sentence which I saw today, the best is yet to come. So this is okay. So finally, I want to finish 5 minutes. So I want to finish my talk with the short wish that I wish you the next 65 years felicidades and happiness, and we can enjoy together. Okay, thank you very much.
Questions?
Yes, I want to know if this magnetometer you build with based on stochastic resonance is competitive with other based on Hall effects or other standard magnetometers. So what is good or better?
No. This was a coil, and we put a magnetic signal, and we detected by short circuit the transitions and the stochastic.
Is faster than other methods, or is
this is the problem.
More sensitivity?
It's in the scientific stage, not yet. We are going to just. I know that. That's why always when in paper they ask to comment, is it faster, is it better, and is it this, like this? But the most important is to discover the scientific phenomenon, and to comment is in this, but you see it's... finally I can say that all the experiments we did during my short visit here, and they are done here in these laboratories which you have here. So you can see that even this nice papers you can produce or make here. I invite of course for cooperation. If any one of you will be interested to cooperate, we are going in the direction of calculated with a tractor, so to logical operation with chaotic circuits, how to perform and this kind. More applications than the so this is like this. Okay.
Yeah. So thank. And last but not least, our last speaker is also a researcher here at the FISC, and he is Tomás Sintes.
Well, I'm happy to see you here, and it's a big pleasure for me to be able to address you and say just a very few words. I'm going to close this small seminar, and it's not expected to be a scientific speech today. And the title means very little. I was expected to entitle it Soft Dark Matter, but this topic is already taken by the cosmologists, so let's make it green. In fact, there was one slot reserved to Professor Joaquin Marro that as you have seen, for personal reasons, it was not possible for him to attend. So somehow I have assumed the, let's say, impossible challenge of replacing him, but I'll try to do my best. And as has been already said today, Professor Marro was the advisor of Raul's PhD thesis, and Raul was mine. In fact, I was his first PhD student more than 30 years ago. As I said, sometimes the beginnings are able to mark a destiny, and this has been my case, and I can be grateful of that. And just to put things in context, and also Maxi did a very nice speech about that. At that time, there was a group, it was created a group of condensed matter physics in the physics department. So there was no condensed matter physics at that time. Maxi came here as a full professor, and with him, his two young PhD students, Emilio and Pera. Soon after joined Raúl, and probably Claudio is there. Yes, Claudio was one, if not the first, one of the first postdoctoral researchers that came around. Yes, not the first one, almost one of the first ones. So after that time, and with, let's say, continuous and determined effort, and aptly with the participation of Raúl, we have been able to build something like the IFISC, that is a reality, a joint research institute between this university and the CSIC, with close to 100 people around, including the staff, that is not more than 20%, but then you add the tenure track positions, postdoctoral researchers, scientific visitors, PhD students, master students, and technicians, and administrative support. And the Institute has been awarded for the second time as a Center of Excellence. Well, you all know the ones that you are here, everybody knows. And an important thing is that we were able to launch more than 10 years ago, something that was a pioneering master studies in complex system in this country, of which Raúl was the first director, and in fact, he has been the director until very recently. Well, he was my PhD advisor, as I said, and that my thesis was about, generally speaking, about the statistical mechanical properties of polymer systems. And at that time, Raúl was working in collaboration with leading and I would say outstanding scientists in the field. Just to mention a few, and it was already said today, Professor Jim Ganton, and also a good friend of mine, Professor Amit Chakrabarty, that he met in his stays at Lehigh and Temple universities. Also his collaboration with Professor Muthukumar from the University of Massachusetts. And it's quite impressive the amount of quality and the number of publications that came with that collaboration in really a very short period of time. So just to make a small overview, all these publications appeared in 1 or 2 years, something like that. Folks. The second is just to put this work into context. I want to say that at the time that this work was carried out, more or less in the same years, fundamental textbooks in the field were published. Not in this case by Raúl, but just to put in the historical context the work that he was carrying out. So this is the book, very famous book on polymer physics, the one that was published by Doi and Edwards. First publication was in 1986. He was working in all these subjects in that years, in 1887, 88, 89, was probably. One very important book is this Introduction to Polymer Dynamics. This one was written by Pierre-Gilles Degens in 1990, and as you probably know, he was the Nobel Prize in Physics for his contribution in this field and other fields like liquid crystals in 1991. That also wrote a very important textbook about the scaling concepts in polymer physics that everyone that has been working in this topic has read at least some time. Thus, what I want to say is that Raúl's scientific production, it has to be stood out in something is because it has been, let's say, at the forefront of the most interesting research lines in the field, in the general field of statistical mechanics and in complex systems as well. And not only that, as a student of him, I appreciate, and not only with me, but pushing the students to the front line, in the scientific point of view. And just I mentioned one of my first conference that I accompanied Raúl to Compiègne in 1991 to participate in this 7th edition of the International Conference on Surface and Colloid Science, where Degens was one of the keynote lecturers. It was, in fact, my first international conference. It's also worth to mention the quality of work Raul did, and also his contributions in the development of novel calculation techniques. For instance, the hybrid simulated annealing, or developing smart and efficient methods to compute random number, or to generate random number generation, that probably most of us that has been working here has benefited from that for many years. I would also like to mention this paper in which he introduced with Chakrabarty and Dickman a novel technique to compute the interaction between polymer molecules using Monte Carlo simulations, a result that I used some years after that to compute the interaction between proteins in cell membranes, and it's probably one of the papers that I like more of mine, of course. Second, also, it's worth to comment that his remarkable interest in communicating science and making to the public, or bringing to the audience, the concepts, the methods, and the applications of statistical mechanics. And here you see just a sketch of just a few of the contributions he did, most of them published in the Spanish Journal of Physics, edited by the Spanish Royal Physics Society. Not to forget about his contributions from the academic point of view. There are 2 textbooks written by him, and if you look at them, you can identify his personal approach to the problems. And as I said at the beginning, every beginning can mark a destiny. So I went back to Google Scholar and see one of his first papers, and this is one of his first papers. So Raul started working on trying to explain some experiments on microcalorimetry in metallic alloys. That was a long time ago. So Raul, we are really on time, so I did not expect that the things were going to go that smooth. So all the people that are here want to thank you. The vast amount of scientific work you have carried out up to date, and as everybody said here, and for the years to come. Thank you. And just one more thing, just to keep you, to remind this day, we have something for you. We have a small present. So, yep. We have a fragile present. A fragile present. No. Es que ahí está. Sí. Que tapas logo, tapas logo.
Thank you very much. I don't know what to say again. Thank you all. There's something else here.
El soporte.
There was some experiment. Okay, that would be nice. I don't smoke. Is that an ashtray?
No. Don't make it dirty. And in room number 7, there will be served an appetizer. Should be ready already. So if you you are all invited to go there. Fan coses molt maques. Sí, és per així. Sí.